Today, we're diving into something that sounds like it's been pulled straight out of science fiction. It's called the squeeze laser, and it's a machine that can, quite literally, manipulate the very fabric of empty space. So yeah, let's get into it.
Okay, let's kick things off with a bit of a brain teaser. Imagine you've got a mirror, but it's kind of crappy. It reflects away 90% of any light that hits it. Now, how could you possibly use that mirror to build a laser that works perfectly, maybe even with infinite efficiency? It just sounds wrong, right? You'd think you'd lose almost all your energy. Well, stick with me, because the answer is truly mind-bending.
And this is the gadget that pulls it off. It's called a squeeze laser. Now, it might not look like much, just a crystal and a mirror, really, but this thing is one of the most sensitive devices humans have ever built, and it solves that impossible puzzle by taking advantage of a loophole in physics, one that lets it control something we usually think is totally untouchable: quantum nothingness.
So to really get how this thing works, we've got to go back to basics. First up, how in the world do you even build a trap for a beam of light?
It all starts with a totally normal laser beam. You can see in this diagram, the beam's most intense right in the middle, and it kind of spreads out as it travels. Physicists call this shape a Gaussian beam. Just think of it as a nice, focused, orderly stream of light. Our first job is to catch it.
So how do you trap light? Well, with mirrors, of course. But these aren't your average bathroom mirrors. By placing two super precisely curved mirrors at just the right distance from each other, you can create a really stable trap. The light beam gets caught, bouncing back and forth, and it's perfectly held in that little space between them.
This whole setup has a fancy name, an optical resonator. And it does more than just trap the light. It actually pumps it up through something called resonance. You know, it's kind of like pushing someone on a swing. If you time your pushes just right at that perfect resonant frequency, each little nudge adds more energy, and the swing goes higher and higher. It's the exact same idea here. As the light waves bounce, they start to overlap. And if that mirror spacing is perfect, the waves add up, and the power of the light inside the resonator just skyrockets.
Okay, so we've got our light trapped, but now we get to the really clever part. This is the trick that solves that whole impossible mirror problem we started with. It's a way to make our imperfect mirror absorb light perfectly.
So with a normal resonator, you're always going to get some light bouncing right back off that first mirror. It's just inevitable. But in a very special configuration called impedance matching, something totally wild happens. You tune the system just right, and suddenly there are no reflections, none. Absolutely zero light bounces off. 100% of it gets sucked right into the device.
And you don't have to take my word for it. You can see it right here in the data. Look over at the graph on the left. See that green line? That's the reflected light. And notice how it never ever hits zero. But now, look at the graph on the right for our impedance-matched resonator. See how that green line just takes a nosedive? Right there, at the very center, at that perfect point of resonance, it hits zero, flat. Nothing is bouncing back. All the light is getting in.
This brings us to the secret sauce. If the mirror reflectivities are identical, no light is reflected at resonance. So get this, the trick isn't having a perfect mirror, it's about having two imperfect mirrors that are perfectly balanced with each other. The light that reflects off the front of that first mirror perfectly cancels out the light that's leaking back out of the resonator. It's an effect called destructive interference. The two waves meet and just poof, they completely erase each other. So from the outside, it looks like nothing is being reflected at all. It's not magic, it's just perfect physics.
Now that we've got this perfect absorption trick down, we can finally talk about what the squeeze laser really does. And this is where things get really weird.
Okay, let's talk about, well, nothing. A perfect vacuum. Logically, you'd think it's just empty, right? Quiet, still. But quantum mechanics says nope. It turns out that even totally empty space is this bubbling, fizzing sea of what they call quantum fluctuations. These are tiny random bursts of energy just popping in and out of existence. This circle you see is a good way to picture it. The uncertainty is random in all directions, creating this constant baseline noise that fills the entire universe.
So the squeeze laser takes that impedance matching trick and points it not at a beam of light, but at this quantum nothingness. The device is tuned so that it becomes perfectly absorbing for all that random noise, but only in one specific direction. It just cancels it right out. But here's the kicker. The laws of physics say you can't just destroy uncertainty, so by canceling the noise in one direction, the laser is forced to amplify it in the other, perpendicular direction. It is exactly like squeezing a round water balloon. It gets thinner in the middle, but it has to bulge out at the ends.
This new state is what physicists call squeeze light. We've literally manipulated the quantum noise. We've taken the uncertainty and, well, we've rearranged it. By making one property of the light, like its amplitude or its brightness, super stable and predictable, we have to pay a price. We have to increase the uncertainty in another property, like its phase or the timing of its waves. We haven't broken the laws of physics, we've just figured out how to cleverly game the system.
So this is all incredibly fascinating, mind-bending stuff. But you might be wondering, what's the actual point? Why go to all this trouble to squeeze nothing? Well, the applications are truly profound.
This technology lets us push the absolute fundamental limits of measurement. You see, that baseline quantum noise creates a hard wall, a quantum limit on how precisely we can measure anything. Squeezed light lets us build detectors that are quieter and more sensitive than that limit. A perfect example is LIGO, the observatory that detects gravitational waves. By using squeezed light, scientists can quiet down that quantum noise and hear the incredibly faint whispers of black holes colliding billions of light years away. And looking forward, this is a key piece of the puzzle for future tech, like quantum computing and unhackable communications.
So the crazy paradox we started with, using two flawed mirrors to achieve a kind of perfection, that's the whole key. It's how we've learned to quiet down the universe itself so we can listen more closely than ever before. This leaves us with one final, incredible question. What new secrets is the universe waiting to tell us, now that we can finally measure beyond its own quantum limit?